All right, today we're going to work problem 1.65, and this problem involves a plate of glass that's at 600 degrees Celsius, and it's going, you can imagine it going down a conveyor belt, and it gets exposed to some ambient air at a temperature to cool it down. Right? And we want to figure out what are the criteria that we need, what's the air temperature that would keep the temperature gradient in this plate material, this glass plate, from exceeding a certain threshold. So this plate is glass and it has a thermal conductivity of 1.4 watt per meter Kelvin, and we know it's at an initial temperature of 600 degrees Celsius. So we have some sort of convective cooling. We're given the heat transfer coefficient of 5 watts per meter squared Kelvin, and this is happening on both sides of the plate. And we also have a surroundings that has a given temperature, and for this problem we're going to assume that the surrounding temperature is the same as the temperature of the air. So these are both equal. So we have a surrounding temperature, we have air at a certain temperature, so we're going to have convection. You can imagine that just because we're given these conditions. We're going to have radiation, so whenever you hear surroundings versus ambient air, the problem is usually hinting that there's some sort of radiation that you need to consider. So this problem is symmetric about the center of the glass plate. Have convection and radiation on both sides, so the heat, half of the heat's going to come out the top, half the heat's going to come out the bottom. So we're going to divide this problem in half because we're only concerned with the temperature gradients in the material, and we're going to draw a control surface around the top of our material. So I'm going to erase these properties here. So what we know is that the T initially is at 600 degrees Celsius. The K of the glass is 1.4 watts per meter Kelvin. Now, as we work through this problem, so we see we have radiation, convection, and we're going to have conduction because we're talking about some sort of temperature gradients being in this glass. There's a couple of things that we really want to pay attention to in this problem. As you know by now, with radiation, Stefan Boltzmann's relation shows that the radiation heat flux is proportional to the difference of the temperatures raised to the fourth power. Because of that, you always have to use the unit Kelvin, degrees Kelvin, in calculating radiation. So we're going to have to be careful to make sure that we convert our values of Celsius to Kelvin whenever we're computing the radiation component of this problem. Otherwise, we would get the wrong answer. What you're also going to find later on, as the math works out, is that the solution is not going to be straightforward. So when you have radiation and you have convection together in the problem, a lot of times you end up having to do trial and error solutions. So you'll see that in a second. But let's start by doing the energy balance at the surface. So we have Q being conducted into the surface, and it's being carried away by convection and by radiation. All right, so if we do our energy balance, we're going to have Q conduction equals Q radiation plus Q convection. Right? So we want to find the temperature ambient, which is the same as the surrounding temperature. We want to find these temperatures that satisfy the criteria that the change in temperature with position X in our glass is less than or equal to 15 degrees Celsius per millimeter of glass material. Right? So you should immediately think, you see this temperature gradient, and that's something that you can plug into Fourier's law. So we come down here and we write out our equations. Normally we write Fourier's law minus k dt dx. There's an area that we must include as well. But this area is going to be the same for all of this. So the area is going to factor out. So I'm not going to include the area. So then we have radiation. So what's our rate equation for radiation? Well, we have surface emissivity. That's also given to us. You probably noticed that if you read the problem. Emissivity is 0.8 times Stefan-Boltzmann's constant times the surface temperature, so Ts here, to the fourth power minus the temperature of the surroundings to the fourth power. And then we have our convection, which is going to be H times the surface temperature minus the temperature at infinity, which is the same as the temperature of surroundings. Right? So I'm going to go ahead and write both of these temperatures as T infinity. And this is ultimately what we need to find. We're going to find this T infinity. Right? Everything else we already know. So if we rearrange this equation, put everything that we know on one side and things that we don't know on the other side, I'm going to erase this, but you should have this drawing now. And right, so we're going to plug in this temperature gradient, 15 degrees Celsius per millimeter, into here. And this term is now going to go to, well, before we plug it in, let's just write it all out. So we have minus k dt dx. Right, so we can bring over this known value. This is going to be now minus E sigma times Ts to the fourth minus bringing over this component, H times Ts. And all of this is going to equal epsilon sigma minus epsilon sigma times T infinity to the fourth minus H T infinity. So we have a fourth order equation, so it's going to be 4 roots. So here's the point where you can tell that in order to solve this, we're going to have to do trial and error to solve this problem. Right? And if we plug in our values, we need to erase that. Plug in our values, then what we're going to get now for all of this is that our dt dx, actually the way I have it defined, that should be minus, is going to equal 1.4 times minus 15 degrees Celsius over millimeter, but let's write it in terms of meters. So this is going to be 15,000. And we're going to plug in for the rest of this. So basically, Stefan-Boltzmann's constant is 5.67 times 10 to the minus 8. We know this value. We know our temperature at the surface is 600 degrees Celsius, but we're going to have to add 273 to that to put it in Kelvin to calculate this correctly. And then here we have our convective term. So we can do all that math. I'm going to let you work through that on your own. And then we're going to end up with a final equation. Plug everything in. You're going to end up with 8,347 equals 4.54 times 10 to the minus 8. So that's Stefan-Boltzmann's constant times our emissivity. And that's plus 5 times T infinity. So there's a T infinity to the 4th power here. There's a T infinity here. So we work through this, we do a trial and error solution, then we shall get that our T infinity equals 420 degrees Celsius, approximately. So that was what I got from my trial and error guess. So the important things here are that whenever you're considering radiation in combination with convection, be careful about the units. You need to use Kelvin whenever you do your radiation problems. And one of the things that complicates a radiation problem is the fact that you often have to do trial and error solutions in order to get your temperature.